because that was during the lockdowns. So
And I'm assuming that you posted it online.
yeah, in one of the videos.
I think I'll just look at that. Those are the homework. I don't really know what I don't. I don't know what I don't. You know what I mean? Like it's kind of.
You should be able to redo the calculations we did in class. Those are your basic titration and buffer calculations.
Yeah.
So make sure you can redo those and that you understand those. And then look at the homeworks. A lot of the homeworks were kind of the same style of calculation, how many milliliters, but most commonly you're given the number of milliliters and then have to talk.
Like optimum pH and stuff like that.
Yeah, optimum pH, buffer, identifying buffers, and this kind of stuff. Okay. If some questions pop up, let me know. But otherwise, we're just going to continue with chapter 18 to try to catch up here.
Will there be equivalent point questions on that too?
Yeah. Yeah, equivalence point. Like, for example, you should be able to do like a monopropic acid tree, like a weak acid, strong base. Give you a curve like this. So let's say we have acetic acid and sodium hydroxide. At the equivalence point, we'll be left with sodium acetate and water. Yeah. And so at the equivalence point, be here, we have a sodium acetate solution. And then we would just do a KB. You know, KB would be acetate and water. And so here we have to do solution dilution to know it. But in this region, from the initial pH to the equivalence point, we can use the HH equation in this entire range here. The only time we can't use the HH equation is like right next to the equivalence point here and right next to the initial pH here. But otherwise, we use the HH equation over the entire range, pretty much. And so this would be like, you know, within like a half a drop or a quarter drop or something like that. Typically, the HH equation works pretty well, you know, from the 1/11th equivalence point, which is down here, you know, to 10/11ths. Between the 1/11th and 10/11th is what we call optimum buffer. But we can go beyond. So we can go past the 10/11ths, almost to the 11/11ths, and still use the HH equation. And so, if we do use the equivalence point here, we can make some simplifications to this. You know, we don't have to do the solution dilution. We can use a shortcut method. And so, let me give you one of the equations for the shortcut method. So if we know the equivalence point here would be whatever, let's say it's 10 milliliters or whatever it is. Then we can figure out what pH is in this Henderson-Hasselbalch region. And pH is equal to pKa plus the log. So one of the equations that we can do is something like this. This would be the log of, X milliliters, however many milliliters we are between here and the equivalence point. So if it's between 0 and 10, it'd be some X milliliters between 0 and 10. Or if it's between 0 and 20, it'd be X milliliters between that. And this would be over the equivalence point milliliters. And so this tells us how many milliliters we've neutralized. So let's say I have 20 milliliters here, and I've neutralized 10, and that's 10 over 20 milliliters have been neutralized, and that would be the base. And then the acid would be the equivalence point milliliters minus X milliliters over the equivalence point milliliters. So as far as another example, let's say the equivalence point were 15 milliliters to get to the equivalence point, and I've neutralized 5. 5 out of the 15 have been neutralized, so I got 5 out of 15 parts base, and then I'm going to be left over with 10 out of 15 parts acid unreacted. And so in this region here, we can just do the Henderson-Hasselbalch. Here, this is like chapter 16. This is just the acid Ka for the acid. Here, this is like chapter 16, which would just be the Kb for acetate. Over here in the excess base region, we'll have to do, step I, solution dilution. That's step 1. Strongest acid, strongest base, and then see what's left over. In fact, we could do all the calculations the same way, step I, step 1. Here, the initial pH, there's no solution dilution. We just have the acid, we haven't added any base. And then step 1 would be the strongest acid, and the strongest base would be water. There's no added base here. But there's shortcuts, even in the excess base region, there's shortcuts you can use, like millimoles and that kind of stuff. But I didn't go through those. I just did it to write them. So you should be able to do like equivalence point. Now, the difference is, this is equivalence point. If we have diprotic acid, then the first equivalence point is an amphoteric species. And so if I have a, like, say, HA minus amphoteric, then I handle that totally different than this equivalence point here. This equivalence point is just a base acetate. This equivalence point, I'm forming, let's say, sodium hydrogen A, whatever that is. And this is amphoteric salt. And amphoteric salt, the pH is equal to the pKa for the amphoteric, which would be HA minus, plus the pKa for the conjugate acid of that, which would be H2A, divided by 2. And then up here we have a dibasic salt for, and so we have a Kb1 and a Kb2, we have H minus left. So we need to know those. Sometimes it gets a little tricky because there are only 2 Kas for diprotic, but for triprotic acid we have 3 Ka values. So which Ka values do you use? So let's say I have monohydrogen phosphate. Monohydrogen phosphate, what is the pH of a monohydrogen phosphate solution? It's an amphoteric salt, so this would be at the first. This would be at the first equivalence point would be dihydrogen. This would be at the second equivalence point in titration for phosphoric acid. And so the pH for this one would just equal to pKa for monohydrogen phosphate plus the pKa for what? Or plus the pKa for the conjugate acid. What is the conjugate acid of monohydrogen phosphate? H2. Yeah. Divided by 2. Otherwise, we would use simultaneous. In fact, this equation comes from the simultaneous method. Okay. Were there any other questions? Let me continue with chapter 18. I think, where did we leave off? We leave off with pH and did we do magnesium hydroxide?
We were doing the combined method, you would introduce the KSPA.
Okay, KSPA.
We did the magnesium fluoride.
Okay.
Yeah. Let me stop there.
And then we know that hydronium likes fluoride. So we'll need 2 hydroniums with the 2 fluorides to make 2 HF plus 2 H2O. Okay. And the K for this equation was equal to
1 over KC parentheses HF versus the second column.
okay. And then we can just combine these. Then once we have it combined, we can do calculations using regularized style calculation. The 2 hydroniums. And we give us magnesium 2 plus. Did I do the buffer calculation?
No, not yet. We just did the K combined, and we got the values of the K combined.
Okay, what was KSPA? This is called KSPA because this is actually KA, inverse of KA. So,
KSP was 0.0849.
oh, KSPA?
Wait, my bad. You're asking for KSP.
Oh, okay. You mean KSPA? 0.0849?
Yeah.
Okay. So the type of question we would encounter is like, if I had a buffer solution, like, what is the solubility? Well, is this more soluble in acid or more soluble in base? So if I have more hydronium, it's going to push the equilibrium to the right. If I have less hydronium, meaning if I have less hydronium, the solution is more basic. So less hydronium pushes it to the left. So I can adjust the solubility. The more acidic, the more soluble. The less acidic, the less soluble. And so I can play around with the solubility of magnesium fluoride by adjusting the hydronium concentration. And so we could pick a hydronium concentration. A higher pH means less hydronium, which means less soluble. A lower pH means more hydronium, more soluble. So we'll pick a pH. Let's say the sample calculation we'll do would be what is the solubility of pH and a pH 4 buffer or something like that.
Yeah, that's what you said.
Okay. pH 4 is just, slightly acidic. Okay, so when we set up the ice table, it's a pH 4 buffer. So a pH 4 buffer means that the H3O plus concentration or the H plus concentration is 1.0 times 10 to the minus 4 molar. So the initial is going to be 1.0 times 10 to the minus 4 molar. And then we're going to have 0 and 0 and H2O is liquid. Now, what we're going to have here is we're going to have minus 2S plus S plus 2S. So at equilibrium, what happens is I'm going to have 1.0 times 10 to the minus 4 minus 2S, but this is a buffer. And what buffers do is they counter, if I lose a little bit of hydronium, they counter it by trying to produce more hydronium to compensate. So if this is a good high capacity buffer, then the pH shouldn't change. And we should end up with about 1.0 times 10 to the minus 4 molar due to buffering action.
Where did the 1.0 times
That just came from this, which is 10 to the minus pH molar. That's 10 to the minus 4, and then we have two sulfates. We call 1.0 times 10 to the minus 4. I don't know what the buffer is, but we're going to assume that the buffer works very effectively. And so if some hydronium is consumed, then the buffer reverses, whatever, and then produces more hydronium to compensate the shot A's, and then we end up with this. This is going to be S molar, and this is going to be 2S molar. So the KSPA for this is going to equal the magnesium 2+ concentration times the HF concentration squared, divided by the H3O+ concentration squared. Okay. And so this is going to equal S times 2S squared, divided by 1.0 times 10 to the negative 4 squared. Okay, let's solve for S here. So I'll do 1 times 10 to the negative 4 squared. Times 0.0849 divided by 4, and then take the cube root. So I get a solubility equal to 0.0005965. And so what we can do is we can plug that back in here and see if our K matches. So I'll plug that back in here. So I'll get this one times 2 equals, and then square that times 0.0005965 divided by 1 times 10 to the negative 8. And I get 0.08489. So it looks like it checks out. So this would be the solubility. Here I'm allowed 2 sulfates. So we'll round this to 0.00060. Molar. So the more acidic I make it, the more soluble it will become. Probably the most powerful way of manipulating solubility is by using KF. And so that was KSPA. We're going to look at KSPF next. F stands for formation of a complex. And so let's take a look at an example here, just a general example. Let's say I want to increase the solubility of silver chloride. What are the ways that I can increase the solubility of silver chloride? It would be anything that shifts this to the right. I'm looking to shift this by Le Chatelier's principle to the right. And so what that involves is removing chloride or removing silver ions. If I can remove silver ions or chloride ions, then I can shift this to the right. Well, then I think, okay, let's look at chloride first. If I want to remove chloride ions, I need to take advantage of the chemical properties of chloride. So what are the chemical properties of chloride? Well, there's metathesis, redox, and acid base. So let's look at metathesis first. What ions does chloride like? Chloride likes silver, and so this can go backwards. But chloride also likes lead and mercury. So what I'm going to do is I'm going to take a look. Does it like mercury? Take a look here. So if we look at silver chloride has a KSP of 1.8 times 10 minus 10. So in other words, the reverse reaction is highly favored here. So chloride really likes silver because it will form a precipitate here. But what about mercury? So if I look at mercury 1 here, mercury 1 chloride is 1.3 times 10 minus 18 versus 1.8 times 10 minus 10. So which one does it appear to like more?
Mercury?
It appears to like mercury more. Do you see that? So let's look at the solubility. The KSP is a little bit tricky because they split up differently. So when I look at silver chloride just splits up into 2 ions, a silver ion and a chloride ion. Whereas mercury 1 chloride splits up into 3 ions, a mercury 2 ion and 2 chloride ions. And so we can't compare the KSPs directly because the solubility depends on either the square root or the cube root or whatever we're looking at. And so let's first look at the solubility of silver chloride without anything. So when we do this, we don't have to set up the ice table, but I will. We'll start off with nothing dissolved, and then this is going to be plus S or plus S. And so we're going to S molar here and S molar here. And so the KSP is equal to the silver ion concentration times the chloride ion concentration here, which is just going to be S squared. And therefore, S is equal to the square root of the KSP. The KSP for silver chloride is 1.8 times 10 minus 10, so we'll just take the square root of that. 1.8 times 10 to the minus 10 square root. Okay. I get solubility of quadruple 0, 1, 3, 4, 1, 6 molar. I'll just carry it for what extra digits, few extra digits there. It should be the same. Well, a mole of silver chloride, this is moles of silver chloride per liter. This would be just 0.400 13416 moles of silver chloride will dissolve in a liter. A mole of silver chloride weighs about 143 grams. And so let's do that. Take that number times 143, and I'm going to get this. I'm going to get, this is 0.0019 grams per liter, which is 1.9 milligrams per liter. So I could dissolve about 2 milligrams of silver chloride in a liter. About 2 milligrams. If I wanted to dissolve 2 grams, not 2 milligrams, how many liters? Well, 2 grams would be 1,000 times more than this, which means I would need 1,000 liters of water to dissolve 2 grams of silver chloride. A 1,000 liters of water to dissolve 2 grams. Maybe I can use less if I can increase the solubility by doing stuff. And so one of the things that I could do is I could put a competing cation. And so let's look at the solubility for mercury 1 chloride and then compare this. So mercury 1 chloride would be Hg2Cl2 solid, and that goes to mercury 1 ions, which are Hg2 2 plus 2 chloride ions here. And we could set up an ice table, although it's not totally necessary. This is going to be plus S plus 2S, so we get S molar and then 2S molar here. So the KSP expression is going to be a bit different. It's going to be the concentration of the mercury 1 times the concentration of chloride squared. So this is going to be S times 2S quantity squared, which is going to give us 4S cubed. And so S is going to equal KSP divided by 4, and then we'll take the cube root of that. So KSP is 1.3 times 10 to the minus 18. 1.3 times 10 to the minus 18. Divided by 4. And then the cube root. The solubility is a bit less. The solubility is 0.60 6875. So it's quite a bit less. And so that means mercury likes chloride more than silver. So if I put like mercury, some soluble mercury salt in here, and I get mercury 1 ions, then the mercury 1 ions are going to be competing for chloride against silver ions, and then mercury 1 should win. What this is called is, it's called a solid to solid conversion. What we're going to do is this. As the silver chloride dissolves a little bit at a time, the mercury captures the chloride, forcing this to shift to the right. Eventually, all the silver chloride will dissolve, but it will be replaced with mercury 1 chloride precipitate. So we're converting one solid into a different solid here, by a solid to solid conversion. Does that make sense?
Yeah.
What about lead? Chloride likes lead too. So if we look at lead-2 chloride, lead-2 chloride is not going to work, because look at the KSP for lead-2 chloride. It's 10 to the minus 5. And although it splits up differently, it's quite a bit different. And so lead-2 chloride versus, in other words, if I put in lead ions here, lead-2 ions, and have that in competition with silver ions would win. We wouldn't have a solid to solid conversion. But solid to solid conversions aren't the cleanest way of dissolving silver chloride, because we're replacing silver chloride, which is one precipitate, with another. That's for chloride. We can also have competition the other way. That is, we can have competition for silver ions. So let's take a look at what chloride, what silver ions like in addition to chloride. So the silver ions do like chloride. You can see here. But silver ions like a whole bunch of other ions as well. For example, arsenate, this is called azide, which is N3-, bromide, carbonate, chromate, cyanide, sulfate, sulfide. Out of all these, which one do you think silver ions like the most? Sulfide. But did I talk about sulfides yet? There's some complications with sulfide. Oh, I forgot to talk about sulfides. Let me talk about sulfides right now. Yeah, for sure. If I put sulfide in here, chloride versus sulfide, sulfide's going to win. For sure. But there's a little, you see, there's a little footnote here, B, for sulfides. So let's see what that footnote means. B, for solubility equilibrium of the type MS solid plus H2O liquid yields Mg plus. Okay. There's something about sulfides. And the situation with sulfide is it cannot dump sulfide. If I put in sulfide in here, something happens to the sulfide itself. Versus, I could put in iodide. If I look at iodide versus chloride, which one does silver like more, iodide or chloride? Iodide. That's 7 orders of magnitude difference there. And so, for sure, iodide. So I pour in some sodium iodide in here. There's a competition now, and the iodide's going to win. I'm going to convert all the silver chloride into silver iodide. But for sure, it looks like the sulfide's the best. But the problem with the sulfide is this. Sulfide is too powerful of a base to exist in water. And so let me do this as a sign here. No. Too strong to exist in water. So what happens is I try to pour sulfide into water, and it's immediately going to have an acid-base reaction. That is, sulfide is going to pluck the hydrogen off water, and it's a strong base. Strong bases are going to react to completion. So water is a weak acid, and so we're going to form HS minus plus OH minus. K is very large for this. So rather than, I try to dump in sulfide in there, but rather than getting sulfide AQ, I'm going to get HS minus, hydrogen sulfide ion AQ. Now, it turns out that hydrogen sulfide can react in a metathesis reaction. What's going to happen is the silver ions are going to knock hydrogen off there. So if silver ions come in, it knocks the hydrogen off, and then we get another silver come in, and form Ag2S. But that's fine, but this complicates things a little bit. Well, that means the KSP equation for HGS is complicated as well, or Ag2S. Is complicated as well. So if we look at Ag2S, because that looks pretty good, Ag2S solid is going to go to 2 silver ions plus a sulfide ion. But we know as soon as we generate sulfide, what's going to happen? Well, what's going to happen is an acid-base reaction because sulfide is too powerful of a base. And so immediately, when sulfide is generated, it's going to attack water. And so we get sulfide plus H2O liquid, and this is going to form, well, sulfide is a powerful base. This is going to form HS minus and OH minus. So therefore, we can't have sulfide in solution. And the KSP equation is going to be modified here. So for every sulfide, we have to have a water. And that's going to produce 2Ag plus in this case, plus an HS minus, plus an OH minus. Okay, this is what we call KSP double dagger. We also have a very weird KSPA equation for this. So we could do, KSP double dagger calculation. If I want the solubility of this, the solubility of this, we can fill out with the ice table. This is pure solid to liquid. This is going to be 0, 0, 0. And so this will be plus 2s, plus s, plus s. And then we're going to get 2s molar, s molar, and s molar. So the KSP equation is going to be the silver ion concentration squared times the HS minus concentration times the OH minus concentration. So it's very weird looking. And so this would be 2s upon u squared times s times s. So working with sulfide is a little bit different because we have a different equation like this. In general, when we work with sulfides, we work with like MS sulfides. This is what they're talking about. This is where M is some metal 2 plus cation. And so when we're working with the MS here, we metal 2 plus sulfide. This is not KSP. This equation is not KSP. Instead, we have to recall that sulfide is too powerful of a base. So sulfide reacts with water to produce HS minus plus OH minus. Then we add these two up. So we have metal sulfide. The sulfides cancel. So we have metal sulfide plus H2O liquid. This yields metal 2 plus HS minus plus OH minus. This is what we call KSP. KSP. Now, when we do the solubility for this one, it looks different. So the initial will be, we'll call 0, 0, and 0. The change in this case is going to be plus s, plus s, plus s. And so the equilibrium that's more, that's more, that's more. And so the KSP for this is equal to the M2 plus concentration times the HS minus concentration times the OH minus concentration, which is just going to be equal to S cubed. So it's just different. So for sulfides, we got to treat these differently. But even though sulfide reacts, we can use HS minus as a surrogate for sulfide, that is instead of sulfide. And HS minus will react to form sulfide as well. Okay, that would be good. But there are a lot of other potential candidates here. So for example, arsenate would be good. Arsenate is pretty toxic. Azide, no, azide would be bad, right? Azide wouldn't work. Bromide would work. Carbonate would work. Chromate, cyanide, iodate would not work. Iodide, yes. Nitrite would not. Sulfate would not. Sulfide would. Those would work in competing effectively, for silverides versus chloride. Okay, but those are solid to solid conversions. One other aside here, let me do one other aside, and that is the KSPA equation. The KSPA equation is going to look a little weird because there are actually two bases here, hydroxide and hydrogen sulfide. So when we talk about KSPA double dagger, the double dagger is like the B for this. And so if we take the KSP equation, which is metal sulfide solid, plus H2O liquid yields a metal 2 plus HS minus plus OH minus. This is what we call the KSP double dagger for generic sulfide. Now, hydronium likes hydroxide. So hydronium and hydroxide will react in equilibrium in the stool form to H2O liquids. When I look at this in the backwards direction, that's KW. And actually, this would be 1 over KW. Okay, the next one will be hydronium plus HS minus, the next strongest phase. And this is going to produce H2S plus H2O liquid. If you look at this reaction backwards, this is H2S plus H2O goes to hydronium plus HS minus. You know what that looks like? That looks like Ka in the reverse direction. So this is 1 over Ka because it's reverse, and it's the Ka for H2S. And so what I end up with is this metal sulfide solid plus H2O. No, not H2O. The H2O is canceled here. And it's going to be metal sulfide solid plus 2 H3O plus yields M2 plus. This cancels the HS minus cancels M2 plus H2S plus 2 H2Os. So this would be KSP double dagger, KSPA double dagger. This would be combined equation. So a typical calculation with the combined equation here would be, give it some pH. What is the solubility of that at some pH? So this would be very similar to the other calculations that we did, maybe in a buffer. In a pH 4 buffer, what is the solubility? Versus the KSP double dagger, what is the solubility in water? That would be KSP double dagger. KSPA double dagger would be what is the solubility at different pHs. And so sulfides are a little bit different, and we have to remember that.
And so the KSPA is what you would do that when they're asking for the solubility of solubility at different pHs.
Yes.
And then you said the KSP double dagger would be for
Solubility in water. And not the different pHs, but just in pure water. Okay, so let's go back to silver chloride. What about adjusting the pH with silver chloride? Could I adjust the pH? That is, could I come up with a KSPA equation for silver chloride? When we're looking at KSPA, we're looking at Bronsted acid. Is silver ion a Bronsted acid or a Bronsted base? A proton donor or a proton acceptor? Silver ion. Silver ion.
Silver ion. It's a proton donor, right?
Well, does it have an H atom to donate?
No, it's proton acceptor.
Well, does it really want a proton? Because if silver ion gains a proton, so if silver ion gains a proton, what would you form? We form AgH2 plus. AgH2 plus, what's holding that together? In other words, is a positive and a positive going to come together and bond together? No. Like charges actually repel one another. And so we don't expect it to be a base. We don't expect it to be an acid, Bronsted. Therefore, we should look at the chloride. What about chloride? Is chloride, chloride's a base, but is chloride a very big base?
I remember reading about those things. I remember.
Well, maybe you remember when I was talking about neutralizing stomach acid?
Yeah.
If you run out of antacid, can you eat table salt to neutralize acid? In other words, if I wanted to neutralize acid, I could just use chloride, sodium chloride, table salt, and that will neutralize the acid. So hydronium like chloride to form HCl and water. Does that look? In other words, is chloride good at neutralizing stomach acid? So if you ran out of antacid, you can just use table salt as a cheap version of antacid. Table salt's a lot cheaper than antacid. Does it work? Why doesn't it work? It doesn't work because chloride is so weak, we consider it neutral. Okay? And so chloride is too weak of an acid. A base. Too weak of a base. And so this one, we can't adjust the pH, for example. We can't make it more acidic. It's not really going to change anything, right? If we make it more acidic or less acidic, it really doesn't change anything.
I remember saying for sodium ions and group 1 ions are acidic.
Yeah.
I know that somewhere.
And the conjugate bases of the strong acids aren't basic because otherwise they wouldn't be strong acids. So Bronsted acid base is nothing going to happen here. This is neutral and that's neutral. So we could try redox. If we do redox, chloride, what are the redox properties of chloride? Well, chloride is an oxidizer or reducer? Yeah, chloride's a reducer. Yeah. What chloride can do is it can lose electrons to form chlorine gas. So we need a powerful oxidizer. If we have a powerful oxidizer, we can oxidize chloride from chlorine gas. Dichromate's not powerful enough. We need something. And probably one of the most common ways that chloride is oxidized is using permanganate. Permanganate is powerful enough. So if we use permanganate, we can oxidize chloride, which is down here, to chlorine gas. Here's another chloride, but it's forming chlorate, or chlorate, which isn't as favorable as chlorine. And in fact, using permanganate in acid is one of the most common ways to generate chlorine gas. One of the most common ways to generate in the laboratory is you take some chloride, like hydrochloric acid or sodium chloride, and you add potassium permanganate to it. And what that does is it oxidizes the chloride to chlorine, and then we can have a little bit of chlorine gas. So we could do the same thing here. We can add some potassium permanganate and some acid, and we'll oxidize the chloride to chlorine. What's going to happen is we're going to remove the chloride. As we remove the chloride and generate the chlorine, it's going to shift this to the right. Now, permanganate is not going to oxidize silver ions. Silver ions are already at their favorite choice. We can use any oxidizer stronger than chlorine. So all these oxidizers stronger than chlorine to do that. That's one way. We can remove the chloride. We can also remove the silver ions using redox. How could we remove silver ions using redox? What we can do is we can have silver ions gain an electron to form silver metal. So that's one way. And so what do we need? Well, we need a reducing agent stronger than silver. So a reducing agent stronger than silver would be like iron 2. So if we use iron 2 will give up an electron to silver and will preserve it as silver metal. Or in hydrogen peroxide. Normally we use hydrogen peroxide as an oxide. But in this case, silver ion is strong enough to oxidize hydrogen peroxide. Silver ions can oxidize manganate, is not permanganate. It can oxidize iodide. Actually, iodide is an excellent reducer. Because if we mix some iodide in there, we're going to have competing reactions because silver will precipitate it, but also silver will oxidize it. Okay. We're going to see which one to do. We did put a strip of copper metal. Probably that might be one of the easy ways to do that. Just put a piece of copper in here. The silver ions will attack the copper, deposit silver metal, shift this to the right. We can use other metals like iron metal, which is even better reducer. Lead, tin, nickel, cobalt, all those are pretty good producers. Zinc, think's much better. But if we do that, then we're going to kind of replace this precipitate with another, which would be silver metal, not the cleanest separation. That pretty much sums it up. We looked at metathesis, we looked at redox, we looked at acid base, but we only looked at one type of acid base. We looked at Bronsted acid base. We didn't consider Lewis acid base. And so what we should do now is look at potential Lewis acid base reactions. And when we do that, we think in terms of complexes in this case. That is, chloride is a ligand. It's a Lewis base. It's an awful Bronsted base. It's so bad we don't even consider it basic. It's just neutral. But chloride can act as a Lewis base and see what Lewis acids it likes. And so let's look here. So this is tetrachlorocadmium, 2. And so chloride likes cadmium, and it can form this tetrachloro complex. Take a look at the K value of that. 630 plus, so 10 squared, that's favorable. And so chloride, that means chloride is a pretty good Lewis base when reacting. Any others here? Here, if there are copper 2 ions present, we don't form, actually this is copper 1, sorry. If there are copper 1 ions present, we form trichlorocuprate 1. This is 10 to the 5th. It's very favorable. What else? Mercury 2. If we put in mercury 2 in there, then we'll form the tetrachloromercurate 2 complex, and look at the K, it's 10 to the 15. It means chloride is a very good ligand for mercury. Lead isn't as good. We'll form the trichlorofumate 2, which has a K value of 24. Platinum's good, but it'd be very expensive. We put platinum 2 ions in there. It's 10 to the 16. Yeah, tetrachloroplatinate. And so what we do here is we put in platinum 2, which would be very expensive. And the platinum 2 wants 4 chlorides. And so we'll have to increase this by 4. And so what platinum 2 plus 4 chlorides is going to yield PtCl4 2 minus tetrachloroplatinate 2. And this is what we call KF reaction. KF is formation of the complex from the metal and the ligand to the KF. If we combine the KF with the KSP, then we'll get KSPF. The combined method works here. The reason the combined method works here, we have 4 AgCl solid plus PT 2 plus 4 chlorides will cancel. Yields 4 Ag plus PtCl4 2 minus. K for this one is equal to KSP, but we multiplied it by 4. So it's going to be KSP to the 4th. And then this is KF times KF for PtCl4. So what we can do is we can, the more platinum we add here, the more this shifts it to the right. The less platinum, the more it shifts it to the left. So we can adjust the solubility depending on how much platinum we add in here. The complex of the chloride. And then, how about silver? That's not really going to compete. So with platinum is pretty high. It's 10 to the 16 versus KSP, 10 to the 10. So that's powerful. So one thing to note is these KFs are huge in general. 10 to the 41, 10 to the 37, 10 to the 31, 35, 10 to the 48. These are big numbers. The smallest one of these is the trichloroplumbate. The trichloroplumbate here is only 24. This is the smallest one of these, but everything else is huge. And so formation of complexes is very favorable. Okay, that's to try to complex the chloride. What if we try to complex the silver ions? So chloride's a ligand. We're looking for what metal ions, what Lewis acids that ligand like. Silver ion is the Lewis acid or central metal. What ligands like silver? So let's go over here and take a look at silver. And there are actually a lot. Cyanide like silver. Ethylene diamine tetraacetate, ethylene diamine, ammonia, thiocyanate, thiosulfate. All those like silver. Which one likes silver the most? Cyanide. So if we put in cyanide here, the cyanide will attack the silver ions. When the cyanide attacks the silver to form the dicyanyl argentate ion, that's going to reduce this, and it's going to shift this to the right. And so we can easily dissolve this by adding cyanide because it's so highly favorable. So cyanide is the best. But the problem with cyanide is it's very toxic. And so let's not use cyanide. Let's use something else. What would be the next best? Next best would be thiosulfate. But thiosulfate is more expensive than ammonia. Ammonia is cheap and it's okay. It's not the best, but it's dirt cheap compared to these other ones. And so let's just use ammonia. And so if we use ammonia here, the ammonia will attack the silver ions and then shift this equilibrium to the right. And so, in fact, that's what we did in lab. You remember doing this in lab? You had silver chloride. Let's say I don't think you generated 2 grams of silver chloride, but you generated some amount of silver chloride. And you ended up dissolving it in ammonia. Do you remember what the concentration of ammonia was? I think you used the concentrated ammonia, is that correct? Yeah.
We had 2 different concentrations of ammonia.
Yeah, we had two concentrations.
So one was like a 16 molar, and then the other was
6 molar, I think. So if I wanted to dissolve 2 grams of ammonia, or not ammonia, 2 grams of ammonia dissolving is easy. If I wanted to dissolve 2 grams of silver chloride in water, 1,000 liters. But what if I used 16 molar ammonia? And so let's do that as a calculation. 2 grams of silver chloride requires how many milliliters of 16 molar ammonia to dissolve? Probably less than 1,000 liters, right? So let's calculate that. So what a lot of people do is they try to do this separately. You know, there's a KSP and a KF. So if we look at the KSP, silver chloride solid goes to silver ion plus chloride plus KSP. We can set up an ice table here. And then we have our KF equation. The KF equation is silver ions get attacked by 2 ammonia to form the diamine silver ion pair. This is our KF. Now, one thing is this. We have 2 types of silver here. We have what's called free silver ion and complex silver ion. So free silver and complex silver ion. And so the total silver in solution here will be the sum of the free silver plus the complex silver. Concentrations. That's the total silver. And oftentimes the total silver is equal to the solubility. You know, if I want to know how much silver dissolved, then I have to sum up these two. That tells me the solubility, so I have to add these up. Normally the amount of free silver is very small because KF is quite large. I mean, this KF is like, what is it? KF value is 16 million. So the KF value is 16 million or 1.6 times 10 to the 7. That's 16, no, that's more than 16. No, this is 16 million. 16 million. That means the free silver ion concentration is very small and the complex silver concentration is very large because this is heavily biased towards product, you know, with a K value of 16 million. We can do the ice here as well. And so, in order to figure out the solubility, we have to figure out all the silver ion species in solution. Well, this is the same, you know, as this. These two concentrations have to be the same. In fact, what we have to do is we have to do these simultaneous. We can't do these separate. These must be done simultaneous because we have to end up with the same concentration of free silver in both equilibria. Otherwise, it just doesn't work properly. And so we end up with the problem of simultaneous. However, this is also a candidate for combined. We can't do everything combined, but when there's certain criteria met, we can do it combined. So the criteria has to be this. The first step has to be
like very small.
very small. The first step has to be very small, the K. And the second step has to be very large. And so the first step here is the silver chloride solid has to break up into the ions. And this K is very small. So what that tells us is not much free silver ion is formed. And the second step has to be very large. That is, the silver ions we're going to attack with ammonia, 2 ammonias, and this is going to form the diamine silver ion. And this K is very large. Very large. And so whatever silver ion that does form is immediately attacked by ammonia. And the end result is most of the silver is complex. When I combine these two equations, what happens is the free silver cancels out. And so what I end up with is silver chloride solid plus 2 ammonias. It gives us the diamine silver complex plus chloride. And this is KSPF. KSPF is going to equal KSP times KF in this case. KSP times the KF. What's missing in the KSPF equation? What's missing is one silver species. We either have the solid silver chloride or we have the complex silver, but where's the free silver ion? The free silver ion is missing out of this equilibrium. Can we ignore it? And it turns out, yeah, we can ignore it if it's very small. And it should be very small because we produce very little, and whatever little bits produced is immediately reactive. And so it's missing free silver ion. And therefore, the solubility is just going to be how much silver, how much complex silver we have in there. Ignoring the free silver. We're assuming it's negligible. What this does is it means we don't have to do this simultaneous. You know, technically we should do this simultaneous because there is going to be a minute amount of silver ions present, which we're ignoring completely. But simultaneous is a lot of work. Combined isn't so much work, you know. So what's the KSP? The KSP was 1.8 times 10 to the minus 10. The KF value is 1.6 times 10 to the 7. 1.6 times 10 to the 7. And then multiplying those together, and I've been having trouble with my phone calculator today. Let's see if I can get it. 1.8 times 10 to the minus 10 times 1.6 times 10 to the 7. Okay, it worked. And so I end up with a KSPF of 0.00288. Okay, now when I do a calculation, it's just one ice table, not multiple silver chlorides, pure solid. And so I'm going to start off with 16 molar ammonia here. And then I'm going to assume nothing's dissolved yet. So it's 0 and 0. And so this is going to be minus 2s plus s plus s. So the solubility is just going to be the complex silver. And there's no free silver. And so we're going to end up with 16 minus 2s molar, s molar, and s molar here. Okay, and then we just solve for s. So this is going to equal the concentration of the complex silver times the concentration of chloride divided by the concentration of ammonia, squared. So that's going to give us s squared over 16 minus 2s quantity squared. Okay, it's likely that, this is not small enough for the simplifying assumption to work, but we'll go ahead and try it regardless. So if I use the SA here, then I'm going to get s squared over 16 squared. So I'll take 0.00288 times 16 squared, and then equals, and then take the square root of that. And I get an S equal to 0.8586. So let's calculate the percent change. The percent change is going to be 2s over 16 times 100%. So I'll take this s times 2 divided by 16 times 100. And I get a 10.7% change. 10.7% means, is the SA valid? No. So SA is not valid. I'll have to solve this without the simplifying assumption. So let's try to solve this without the simplifying assumption. It's going to be, I'll write it up here, 0.00288 is going to equal s squared over 16 minus 2s quantity squared. So what should we do? Should we get it into quadratic form? Quadratic form? Take a look. So I guess I'll just multiply out this binomial here. Maybe 4s squared, 32, 64s, and 16 times 16, whatever that is, 256. 256. So I can easily get this into quadratic form, which I was about to do until somebody said there's an easier way. Do you see an easier way? No. Well, again, me too. I didn't see it earlier. I've seen it before. The funny thing is, I think it's done this problem many times. I've done it by the easy way. I just forgot the easy way. Sometimes it's hard to see. It's hard to see because you don't use it that often. You use it often, and it's easy to see. Right? But I don't use it very often. The easier way is just to take the square root both sides. You see that? Yeah. I know, I missed that too. Because I don't use it that often. And so that means the square root of 0.00288 is equal to s over 16 minus 2s. And so what is the square root of 0.0288?
0.05366.
0.05366.
Yeah, 56.
56. Okay, that should be enough. Is equal to s over 16 minus 2s. So we'll do 16 times that. So 536656 times 16. So we got 0.8586. 4 minus 2 times that. 2 times that. That's going to be minus 0.10733312s. is equal to S. And then let's add this to both sides. We're going to get 0.85864 is equal to 1.1073312 S. And therefore S is equal to um, 85864. 3.9999. Is that what you guys get? Yeah, okay. I've been having trouble in my calculations lately. Let's see. Let me try it again. 0.85864, 0.85864 divided by 1.1073312. Oh yeah. I got it too. What did you get?
0.7754.
Yeah. Okay, we'll just carry one extra just for good measure. Okay, and so this is the solubility. So the solubility increased dramatically compared to what it was before. In fact, if I do this, I'm going to do the same thing times 143. What this means is 110 grams, 110.88, or 111 grams will dissolve in a liter. What did we have before? We had 2 milligrams to dissolve in a liter, and now we can get 111 grams to dissolve in a liter. So dissolving 2 grams is going to take way less than a liter, versus dissolving 2 grams would take 1,000 liters of pure water. Dissolving 2 grams of silver chloride, well, let's figure out how many liters it's going to take. In fact, since it's going to be less than a liter, let's figure out how many milliliters it's going to take. So we're going to use this here. This is the solubility. We're going to use this solubility to calculate this. So if I wanted to dissolve 2 grams of silver chloride in this, then I'm going to convert this into moles first. And it's 143.32. Well, we'll just go 143. This is just a rough calculation. Grams per mole. Or 143.32 is not size, but I don't have 1, 2, 3 here. And then I can dissolve in every liter, I can dissolve 0.77541 moles. 0.77541 moles weighs 110 grams, 111 grams. And then I'll convert it to milliliters. So this is 1,000 milliliters per liter. And so this will tell us how many milliliters of 16 molar ammonia is required to dissolve 2 grams worth of silver chloride. And so we go 2 divided by 143 divided by 0.77541 times 1,000. 18.036 milliliters times 20 drops per milliliter. Would be 300, that's a lot, 360 drops. 360 million drops. So I wouldn't use a dropper to dissolve it. However, if I were to dissolve 2 milligrams, if I wanted to dissolve 2 milligrams, which would be 1,000 times less, I'd only need 0.3 drops, not even 1 drop to dissolve. A third of a drop. Versus if I wanted to dissolve 2 milligrams in pure water, it's 1,000 liters. So here it's tremendously more soluble. So ammonia, even though ammonia is not the best, ammonia is highly effective at dissolving silver chloride. If we had 16 molar cyanide, we'd use a lot less for that. And so 18.036 milliliters of 16 molar NH3 is required to dissolve 2 grams of silver chloride. All right, that's the end of chapter 18. What we're going to do is we're going to drop back down to chapter 13. And chapter 13 is thermodynamics part 2. So let me just talk briefly about this. I don't know how much time. Normally when we think about driving force for reactions, what is the driving force? Stronger acid or weaker acid? Stronger base to weaker base? Stronger oxidizer, weaker oxidizer? Well, what we're talking about there is in terms of energy. Less stable, more reactive, higher energy, going to more stable, less reactive, lower energy. But that doesn't always happen. When we think about the ball always rolls downhill, right? But in some reactions, the ball actually rolls uphill without anybody kicking it. So how can the ball roll uphill? If you think about some reactions that occurred like cold packs, if you have a cold pack, there's nobody pushing that reaction uphill. It's just naturally going uphill because what's happening is you're starting off with lower energy and going to higher energy and sucking energy out from the surrounding. So it turns out when we look at this is in chapter 13, we're going to quantitate the driving force for reactions. Earlier we were just looking at it qualitatively, and it turns out there are 2 driving forces. Technically, there's only one, which we'll talk about later, but we'd like to divide it into 2 driving forces for it's just easier to understand. 2 driving forces in nature. And what we've been focusing on is energy, because the first driving force is to minimizing energy. Minimizing energy, we want to go downhill, so the ball rolls downhill. We want to minimize gravitational water flows downhill, minimize energy. Not energy is gravitational potential energy. But there's one more driving force, and this is what causes balls to roll uphill without anybody pushing it uphill. And what causes balls to roll uphill is maximizing entropy. So we can have the ball roll uphill or be pulled uphill by entropy. Entropy, what that is it's a measure of disorder. So the higher the entropy, the more disordered the system. It's also a measure of constraints, measure of disorder. So more disorder, more entropy. Fewer constraints, more entropy. The more constrained the system is, the more constrained the system is, the more ordered it is. So if everything belongs in a specific position, and it's not there, then measure of disorder or constraints. Constraints, we want fewer constraints. Pure is higher entropy, more constrained is lower entropy. Now, energy is a bit more trickier than people remember, because we have different types of energy that we look at. We have E. E, people think of as total energy. And total energy is equal to the sum of the kinetic energy plus the potential energy. That would be the total energy. The kinetic plus the potential. But we also had other symbols for energy. One of the symbols is U. You recall what U stands for? U stands for internal energy. And then H. You know what H stands for? H stands for enthalpy. So what's the difference between internal energy, total energy, and enthalpy? What's the difference between these? Or are they all the same thing? And so this is what makes thermodynamics difficult, because people don't know the basic definitions of these. So if you don't know the basic definition, that is, if you don't know the difference between U and H, how can you do thermodynamics? And so this is why thermodynamics has a notorious reputation. Thermodynamics will be the next class after organic chemistry, has a notorious reputation as being a very difficult class. The fail rate is very high. So what you have to do is you have to go back to chapter 7 and look at these. And so go back to Chem 1A, chapter 7, and take a look at what the difference is. Otherwise, we're going to be using the wrong thing at the wrong time. Okay, I'll stop here since we're out of time.